So thanks to all that are here currently. My name is Troy Robichaud, and I am the Events and Engagement Lead at the European Biochar Industry Consortium. And of course, today we are here to explore the topic of biochar permanence. So as far as my role with the EBI, events and engagement is one area that we're growing in activities with our growing capacities. And that's what I'm leading now over, I guess, since the middle of October. I know Harald had started a webinar series, I believe, since day one with EBI, and with that growing capacity that we're always having. Webinars are one area that we're seeing so much success in as far as connecting key topics and key people. So that's one area that we're really starting to grow and invest our time more and more into. So over the next 3 weeks, of course, as I mentioned, we're going to be talking about the permanence of biochar, of course, hosting Professor Hamed Saneh of Aarhus University. So I have a few things I'd like to go over just before we get started. So today's topic, we're going to be focusing mainly on the carbon cycle, and Professor Saneh is going to dive deeper into that topic. Next week, we're looking at the inertinite benchmark and the introduction of it, as well as some of the inners of Professor Saneh's work over his latest published paper. And of course, our third webinar is going to be focusing on kind of the recipes of pyrolysis to explore, how we can be maximizing carbon capture with our biochar production. So for today's format, I'm going to hand it over to Secretary General of the EBI, Harald Beer, who is going to kind of introduce the topic, introduce Professor Saneh, and just lastly, I'll ask that everyone please hold your questions until after Professor Saneh's presentation. Because we have so many participants, we'll be looking through the chat and kind of working internally to make sure your questions are presented to Professor Saneh through there, just to make it a little bit more manageable on our end. So without further ado, Harald, take it away.
Thanks a lot. And it's very nice to see so many of you. I just said it before, it was really difficult to not say hi to all the different names that were coming up. It's wonderful that we see such a response to this information we're trying to provide. And this is just I don't want to give too much of an introduction of Hamed here. I guess most of you have Googled him. Maybe he's one of the most renowned experts in the field of organic geochemistry. And for me, only thing I wanted to say is like how we got together. It's this entire journey started about 2 years ago, while we have already been discussing biochar permanence for about 10 years, and there always seemed to be like something lacking to complete the picture. And as EBI, we were expecting that based on our limited knowledge on kinetics, that commonly produced, industrially produced and available biochars, they would have a hard time degrading within these timeframes that have been discussed there. So to us, it was the time to ask geologists. And then luckily, about 2 years ago at a conference at Roskilde University in Denmark, we were both presenting. Actually, it was Henrik also. So all three of us. And after the presentations, we got together and we, exchanged a little. So I learned a lot. And to me, it was the first time discussing biochar permanence with geologists. And my take definitely is that we can't even discuss permanent carbon removals of any sort without having a deep understanding of the natural carbon cycles. And this is why we're here in this first webinar of a series of 3 to understand the carbon cycles. And I'm very happy that Hamed was agreeing to presenting this to us. Thanks, Hamed. I'll just leave you the stage.
Well, thank you so much for the introduction, and thank you, Troy. Hi, everyone. It's a great pleasure and honor to be able to present this webinar to you. So I'm going to share the slides. So we start. It's going to be hopefully less than half an hour. It will be short. Today, which is the first session, as mentioned before, we're talking about the geological carbon cycle perspective and how it is related to the biochar and biochar permanence. I'll explain to you why it is important, particularly in the absence of empirical data for measuring permanence during the short period of time that we have for the experiments. So that's really the focus of this session. So I'd like to introduce my good colleague and research partner, Dr. Henrik Peterson of Geological Survey of Denmark and Greenland GEUS, who is together we lead these biochar projects and the funding of GEUS, Geocenter Denmark, and also, of course, the tremendous in-kind support of the EBI with linking us to the industry samples and all the support data and information that they could provide. And mentioned that there will be 2 other sessions on February 26 and March 4. So basically, these 3 sessions together unpack the paper that we recently published assessing biochar's permanence, the inertinet benchmark. So it would be really helpful, at least if you attend the 2 sessions where we explain most of the paper and we go a little bit beyond, especially try to focus on the areas that have been misunderstood from what I've been basically informed. Special thanks to Harold. Harold is my to-go person, is an encyclopedia of biochar, technical aspect of biochar for me, and a great support and link for acquisition of samples and data from industry that has been really made us able to do this research. And a special thanks to Professor David Chiaramonti, who's we often discuss biochar, and his perspective has been very helpful. And some of the ideas that we exchange, it has basically crept into this presentation, and I'm going to talk some of the things that have been inspired by discussion with him. So I'd like to thank them all. And let's start the actual presentation. Since we're talking about carbon cycle today, carbon cycle for most, particularly if you search on the internet and where it is being taught in schools and universities even, it's often the cycle that we call it the biosphere cycle. So where we see the CO2 is being basically processed by photosynthesis through the biomass, and then it cycles through the biosphere. And of course, the big culprit of climate issue and the rise in the CO2 is geology. So it's fossil fuels and carbonates for where it is being used for cement production, and this is basically the disruption in the carbon cycle as we know of and as we deal with it. So it's very natural that geology is often seen as a part of the problem, not the solution. So given this idea that the geological carbon and release of those in the biosphere has led to the climate problem, one obvious solution that has been proposed and now is widely at the industrial scale being applied is putting the CO2 back into the geology. And that's basically carbon capture and storage, CCS method, which uses the concept of physical trapping of CO2 by geological barriers. So there is nothing stable about supercritical CO2. It's under pressure, highly pressurized and in fact reactive and corrosive. But we bet on the geological barriers and the rocks to provide the storage security. So of course this is one method that produce carbon CO2 storage at a huge scale, gigaton scale. But the question is, how does Earth would process the removal and storage of CO2? It never works in a way to open the Earth and the CO2 being all of a sudden incorporated into the geology. The carbon cycle from the geological perspective is more complex. It consists of two cycles, in fact. One in a biosphere where carbon has a shorter turnover of annual to millennial time scale. There's also a smaller carbon pool, about 47,000 gigaton of carbon, which you're familiar with it, carbons in ocean, atmosphere, permafrost, terrestrial vegetation, soils, and so on and so forth, where you are familiar with this. These are what we are dealing with in the daily life. And this cycle is intertwined with the geosphere carbon cycle, where there is much larger, in fact, gigantic pool of carbon is stored in there, about 80 million gigaton of carbon. And the turnover of carbon is at a multi-million year time scales. Most notably, limestones, sedimentary organic matter, coal, oil, and gas. These are what you're familiar with. So the question is, how does the carbon goes from the biosphere into the geosphere? It goes through the geochemical or biogeochemical transformation, where the molecules of carbon is being transformed into the geosphere through what we call it diagenetic interval. That is where the biosphere and geosphere are in contact with each other. And it goes anywhere from the surface soil or surface sediments all the way to 2 kilometers, where the bacterial degradation and biological activities become very limited or maybe even entirely prohibited. That is when the carbon is no longer being degraded or being cycled through biosphere, and it will be transformed into geosphere. And it's a geosphere processes that exclusively are in place to cycle carbon in the geological cycle. So basically, in order to open up more what happens in a diagenetic interval, I have this simple chart where the CO2 in the biosphere goes through the process of mineralization. Many of you are probably familiar with this. Mineralization of CO2 happens through the process of chemical weathering, or more famously called silicate or carbonate weathering. And that is how CO2 from biosphere is converted to the carbon minerals. Well, of course, these carbonates or carbon minerals are responsible for large quantity, as I mentioned, about 65 million gigaton of carbon in the Earth's crust in the form of limestone, basically. That's a big process. But one process that surprisingly is less being acknowledged is the organic carbon pathways, where the CO2 in biosphere through the biomass is incorporated into the geological process by the process that is called maceralization, and that becomes a carbon macerals. So this process is done through either a slow carbonization, which is called organic carbon maturity, and the second one is a rapid carbonization. Essentially, the end product of this maceralization is the organic carbon compounds or macerals that are regarded as inertinides. Essentially, this organic carbon pathway is responsible for another gigantic pool of organic carbon in the Earth's crust, about 15 million gigaton. So carbonates and inertinides are the two sides of the coin. They are the end product of the carbon cycle, going from biosphere to the geosphere. They are the most thermodynamically stable form of carbon, and that is why they are basically stored permanently and form permanent carbon storage in the geological time scale. So it's really important to know there are two pathways, inorganic and organic carbon pathways. But you often always hear mineralization as a permanent pathway, and these pathways is being somehow overlooked for the reasons that are not really known to me. So let me a little bit more explain the process of mineralizations. As I mentioned, a slow carbonization, it happens due to burial. Any organic carbon that is formed on the surface eventually would be buried. If it is on the soil or if it is in a sediment, it will gradually get buried. And as it is buried from surface all the way to near 2 kilometers, the process is diagenesis, which is dominated by bacterial degradation, and organic carbon continuously release CO2 and methane. After 2 kilometers, geothermal heat would increases in that depth, and that is when only geological process, mostly pressure and temperature, are responsible for degradation of organic carbon. No more bacterial degradation, and that process is called catagenesis. And then at 5 kilometers deep, essentially organic carbons become so stable and non-generative, and that is the process or a stage that carbon becomes goes into a stage of metagenesis or metamorphism, where the sedimentary processes are no longer capable of degrading organic carbon. So essentially what happens, the organic molecules become fortified through this process, becomes aromatized and condensed from more kind of more labile, more active organic to extremely stable and inert form of organic carbon that are very difficult to be degraded by shallow surface processes such as bacterial degradation. So this process can be actually shortcutted by rapid carbonization. So we don't need to go through all these massive processes. And the rapid carbonization, in particular charring or formation of chars in the wildfire, that is oxygen depleted fire or heat of the organic carbon in the wildfire, where it forms material which is charcoal, more informal language, but in a geological term is called also inertinides and has the same stability and rigidity that inertinite has during the slow carbonization. So we see these inertinides more particularly if it is from the woody material in geology is called fusinite. We see them everywhere in virtually every form of sedimentary rocks that you could imagine, in a coal, in a shale, in a mud rocks, siltstone, even sandstones, even limestone. So you see these ones scattered virtually all over any sedimentary rocks throughout the Earth's crust. And the question is, how are these materials being preserved so fabulously through hundreds of millions of years? And that goes back again to the process of burial and deposition of organic carbon in the sedimentary basin, where all these materials at once they were on the surface, they are formed on the surface, they settle on the land, on the soil, and then eventually they are washed into the sedimentary basins, into deltas, reefs, marine sediments, lake sediments, rivers, or even just vertically going down through the soil profile until it becomes buried. And this burial process would result in the fact that these materials would end up eventually at much deeper depths into the lithosphere carbon cycle, where we see them, and they're ultimately responsible for massive quantity of carbon being preserved in the reservoirs. Well, how this long introduction relate to the biochar? Well, biochar uses the process of pyrolysis at much higher and more efficient temperature. So the biomass is converted to biochar after, of course, release of energy and material through syngas or pyrolysis oil. But this biochar biogeochemically and optically microscopically has the same properties as the inertinite, as I described earlier. In fact, biochar has a known properties where with increase in the pyrolysis temperature, the degree of aromatizations and condensations, and of course fortification of the molecules of carbon would increase immensely with increase in temperature. And one of the proxies that widely used in geology to determine the degree of aromatization and condensation is random reflectance, which I will explain in great details in the next session, the session number 2. But the point is, increase in random reflectance means rapid increase in stability of the organic carbon as the pyrolysis temperature increases. And we know that at a reflectance of greater than 2%, in fact, organic carbon turns into inertinite, the same inertinite that is found in great quantity in the geological rocks, and it is the benchmark of or end product of organic carbon cycle. So this provides an indication that the biochars would produce the same kind of material. And in fact, our large survey of over 60 industry biochar samples have shown, where we also published it, that up to 76% of all the industry biochars were pure inertinite. They have the same geochemical, same molecular and optical characteristics as the inertinite. So this is something that I will talk more extensively in a second session. So, but what's the difference between the biochar that is not fully carbonized and the biochars that are fully carbonized and we regard them as pure inertinite? So the ones that are partially carbonized, in fact, they have several organic fractions or organic pools. And again, that's something I will extensively discuss in the next session. But just to give you a very quick summary here, there are 4 fractions present in the partially carbonized biochar. The first 3, which is also regarded by many experts as a labile fractions, are the condensate. These are the secondary oil fractions that will be condensate on the biochar vacuoles. Then there is a fraction which is liptinite, which these are basically semi-charred hydrocarbon-rich fractions of biomass. And then semi-inertinite is the carbonized woody material that has not reached the degree of inertinizations. And then we have quite a dominant fraction of inertian. So there are really 4 fractions where you could imagine 3 of these 4 fractions could potentially be cycled through the biosphere but the fraction of inertinite is only being cycled or is only being subject of process of geosphere. It's not going to be subject of processes in the biosphere. The other organic pool in the inertinite, pure inertinite biochars, and these are the biochars that we identify predominantly produce at temperature of over 550 degrees centigrade. So these biochars are fully carbonized. So as you could see, the fraction 2 and 3 are not present. It's only fraction 4, which is pure inertinite. But even these, they would have very small, something around less than 1.4% as we measured in our survey. Condensate. These condensate are secondary and they would trap during the cooling on the biochar. So you could not escape from these no matter how you form your biochar. So as you could see, even the inertinite biochar, pure inertinite biochar, may be subject of a small fraction of organic carbon that could be biodegradable, readily biodegradable, and would cycle through the biosphere. But predominantly more than 98% is pure inertinite, and thermodynamically should not be cycled through the biosphere, and is only capable of degradation in the geospheric processes. So let me open up this one more. The issue of biochar persistence experiments. So how can we actually, considering these different fractions, we quantify, we experimentally measure the degradation of carbon using bacteria? Well, since the application of biochar, the importance of biochar is more dominantly for soil, naturally soil lab incubations are the most important process to demonstrate potential degradation and permanence of biochar. Well, there are two methods: field trials or lab incubations. The labs are closed system, and for knowing the mass balance of carbon, this is the only method we have that is not subject of erosional loss. So let's see what these methods are telling us. There are near over 100 studies of the lab incubations, all state-of-the-art experiments that have been conducted trying to measure the actual carbon loss during the incubations experiments. A great paper by my good friends and colleagues, Azi et al., very recently released, which shows the actual data. I'm not talking about the model part, but the cumulative decay over experimental durations. These experiments are mostly around 1 year experiments, and some goes to few years. I think the longest goes to 8 years that has been published, 8.5 years. But when we isolate the biochar samples that are produced at greater than 550 degrees centigrade, where we regard them as more inertinite biochar, we see the cumulative decay of these biochars are for many of these studies. You would see it would decay through the experimental period, but the actual amount is something we should note. It really goes in 1%, 1.2%. Even the ones that are the biochar that are produced at lower temperature, we are talking about less than 5%. Some maybe a little bit more, 6%. But these are the numbers that we are dealing with. So what I'm trying to say here is we have a problem where we cannot accelerate these experiments to see the decay of the entire biochar by bacterial process within a reasonable experimental period, which is, let's say, 1 year, 2 years, and 2 years. So we see only very small fraction of the biochar decay, And that is the basis of our empirical data, where we're going to base our model on those empirical data. Let me basically give you an analogy of what we are dealing with. If this is the time of the experiments, that incubation experiments in years, and this is the degree of carbon loss going from 0%, think of the biochar like the inertinate fraction like a concrete ball. And the labile fraction, such as the condensate, think of it as a peanut butter coating the concrete ball, which is our inertinate. So when we conduct the incubation experiments, obviously and naturally the bacteria would start degrading the peanut butter. This is because it is more reactive and is thermodynamically is preferred material for bacteria to degrade. So what we have been seeing in empirical data in the measurements done by incubation studies, we see something, these peanut butters are degraded from 0 to 1, 1.2, let's say even maximum 2, 3, 5%, but that is the limit of our empirical data. And of course, the modeling is done. There are different type of models, but they're all done based on this level of empirical data. But the problem with that we are facing, and it's by no means is a problem of the studies that people have done. It's the general problem dealing with biochars, is that the inertinate fraction or the concrete ball doesn't even begin to be degraded in such a short period of time. That means we would be left with no empirical data during the experimental study, and of course our projection would be based on no empirical data. So this is really the problem we are facing. So that means our projection is based on the scenario assuming the entire thing is the peanut butter, and disregarding the concrete ball in the center. And that's pretty much the same when we are dealing with the scenarios of the biodegradations and incubation studies and projection models that we are dealing with. So you may ask, so what's our solution? Like, in the absence of empirical data, how can we understand or measure or infer the permanence of the biochar, where it's predominantly composed of inertinite? For that reason, I'll bring these geological perspectives. So geological perspective becomes very important in the absence of empirical data. And I give you an example. For instance, in a CCS, where we are trapping CO2 through geological barriers, which is called physical trapping, the geological perspective for permanence that we use, or scientists use, is that geology have kept the fluids, water, oil, and gas, under these geological barriers or rocks for millions of years in this reservoir. So if that is the case, then it should be able to also store the new fluids, in this case CO2, into the geological rocks, and it should not go back up. So it has a permanent storage capability. So this is the geological perspective that is being used for the CCS. So now, in the absence of empirical data for biodegradation of biochar, so we have a very similar situation. We know that biochar transforms CO2 by biogeochemical trapping, and it's really the molecular barriers that would store the carbon, irrespective of where it is being applied, on the surface or on the depth or in being buried. It doesn't matter. What is really important is that inertinides have been preserved for millions of years, and thermodynamically, they are the most stable form of organic carbon in the sedimentary rocks and on the Earth's crust. If inertinides would have been degraded in 100 years or 200 years on the surface, then I could rest assure you that there would not be any organic carbon preserved in any form of sedimentary rocks. That means the surface processes would completely degrade, and all organic carbon going from the surface into the diagenetic processes would be or would have been completely vanished. And this geological perspective is very important for understanding the inertinide benchmarks and the studies that we've done, and I will explain in these 3 series, in the remaining 2 series of this webinar. So, and this is the last slide. Given that geological perspective, the main and most important question comes that what is the size of the inertinide fraction, particularly if the biochar is not fully carbonized and is not completely inertinide. So we do have very conventional and readily available methods in our hands to be able to measure and estimate the fractions of inertinide in any biochar sample, and these methods are readily available, as I mentioned, that can be used to define the storage capability of the biochar in question. I'd like to thank all the co-authors of the paper, in particular Professor Soren Nilsson and Dr. Arko Rudra, who I mentioned my colleague Dr. Henrik Peterson in the beginning, and of course a young team of very ambitious and intelligent students that have been helping us throughout this process and are co-authoring this paper. I can end here, and if there is any questions, Troy, I'll leave it to you.
Great. Thank you so much, Hamed. Really, really interesting. I was able to hear Hamed speak at Bio 360 a few weeks ago, and always fascinated how clear he's able to deliver information and make it digestible for everyone. So thank you. I'll leave it now open for questions. As I mentioned earlier, I know some people kind of trickled in later. We're going to take questions in the chat, and I'll facilitate those to Hamed here. Just making it a little bit easier as we have quite a good turnout today. So please write your questions in the chat, and I'm sure we'll do our best to have them addressed.
It was quite something, huh? To have an intro into geochemistry. I think that's quite challenging, and luckily we recorded it so people can watch it a second time. I've heard quite a bit of it beforehand, so to me it was all really understandable. But I think you. Before we have questions in the chat, maybe I can address one thing that seems to stir up or to create quite a bit of confusion here and there, and that is somehow you have the organic and the inorganic carbon pathway. Now, the first thing that comes to mind is probably organic seems not to be as persistent as inorganic, because you think of biomass somehow. Maybe you can kind of elaborate a little bit more on that. And then the other thing is what you were saying is when you were talking about the preservation of fusinite, which basically is biochar but through natural processes. So decent grade biochar, maybe not the most inert form that we would normally produce in advanced technology. But you referred to burial as one of the key processes when you talk about organic carbon. So maybe there would be a need to clarify, what if you took that material after it went through kilometers of the Earth, if you would just take it back out and leave it sitting there? Because I think that's a question that always arises.
Yes, I may need you to repeat your first question, but let me explain the second question. In fact, nature has done that for us. These geological rocks are being pushed up through the process of uplift, and you see them everywhere. Many rocks and mountains or cliffs or rocks around you are sedimentary rocks, and these organic carbons have been exposed for millions of years on the surface. So they're not being degraded. There are other fractions that should be thermodynamically they are preferred to be degraded. Per definition, inertinite. We didn't come up with the name inertinite. It's a name established for many decades, known by coal geologists, organic geochemists, organic petrologists. So it's a very well-established terminology. So these compounds, these materials have been preserved. They're widespread. You would see everywhere in the geological rocks, in the even shallow sediments. So I mean, I have to flip the question the other way around. If these are being degraded, then there would nothing be able to be preserved, because these are the most stable, thermodynamically most resistant form of organic carbon. There should be every other forms of organic carbon be degraded before we reach these material. So as I said, it's very difficult because we don't have empirical data. We don't have thousands of years to actually degrade that concrete ball, to be able to show you what's the degradation pattern by bacteria. Nobody does, and the empirical data has shown, very small fraction degradation, most likely related to the peanut butter coat. So in the absence of this, we really use this geological perspective to argue about the permanence of carbon. And I think the first question was about mineral and versus the organic macerals. Yeah. And why it is not being publicized. Is that what you ask?
Yeah, I think how do they stand in relation to each other? Because we say, oh, organic, yes, but we know that the inorganic, like limestone, like Tom Walsh, I see in the chat, asked, how is it in relation to limestone? Because there, it is permanent, but
the both are the ultimate material that are being used to store carbon in the Earth's crust. Mineral carbon is basically the end product of inorganic carbon cycle, and that's how carbons end up being stored in the form of rocks. And organic carbon cycle in the same way, process of converting organic carbon into the macerals through the diagenetic process would result in a storage of organic carbon. And that's why we have 15 million gigaton of organic carbon in the sedimentary basin. So there are two sides of the coin. Chemically, they are not related to each other, but they are part of the process.
Thanks a lot.
Great, thanks, Hamid. Just getting into the chat here, I'll start from kind of the top. The first question is regarding lab availabilities. This question's regarding India, but I'm wondering, Hamid, through your networks and maybe from a European perspective, what kind of labs are out there looking at biochar and inertinite perspectives, inertinite percentages in biochar?
Well, currently we are doing it. It's not very unique capabilities. I'm sure there are many labs that they could be potentially doing the same things. But since this is dealing with a new material, the biochar, so we are accelerating the process to make it very relevant for determination of inertinite fractions and also upscaling it. So yeah, please contact me and I'll help you on that.
Great. We have a question here from Marcel. He writes, Hamed, thanks again. Could you please explain whether random reflectance does directly or indirectly measure the stability?
It's actually the only method that is calibrated for degree of carbonizations throughout the Earth's history. I mean, you cannot find any other proxy that is so well calibrated. And I explain to you why, because it has been measured in hundreds of thousands of rocks, sediments and rocks throughout the whole world essentially by coal and oil and gas industry, by fossil industries. But these data have been available, and these rocks that we have the random reflectors measured are coming from different depths, different temperature. They're coming from diagenetic stage, catagenetic stage, metagenetic stage. So we know at every RO values what stage, what temperature, what geological or geochemical conditions those rocks have been. So not only directly random reflectance is related to the carbonizations, to the aromatizations and condensation of molecules, but it's well calibrated with the amazing, tremendous geological records in terms of stability and permanence. So it's not directly related to the permanence in terms of how many years related to the random reflectance. But you know, if you have a random reflectance of 2, you have to be at 5 kilometers deep at a tremendous kind of conditions that is not available for the surface or biological processes. So I'll leave it to that.
Great, thank you. We have lots of questions. I'm trying to filter through what the most relevant are for today's discussion.
Should I raise one then quickly? Because I'm just seeing when you mentioned on your slide that 76% of the industry biochar is pure inertinite. Is that fraction the same as what we call, is the question, the persistent aromatic carbon? So the PAC, this discussion, I think you know this. Is this the same as inertinite?
I am pretty sure if you measure the fractions of inertinite in a biochar, and you measure those proxies or those quantities of what you mentioned, a stable, what was the name? Persistent aromatic carbon. And if you measure the quantity of fixed carbon and you measure the carbons with the high what you call it, the graphitization band in Raman and many different proxies, they're all going to give you beautiful positive correlation. These are all correlated with each other. But if you tell me if they are directly one-to-one related, I don't know. That requires us to basically do the measurement of SPAC on the same sample that we've done random reflectance and done all other analyses and compare. And then I can tell you the relationship is one-to-one or what's the conversion regression between the two. But in principle, it's the same things. The increase in the random reflectance is caused by increased aromatization and condensation, is ordering of carbon. And that's in principle what a SPAC is. So it should be highly relevant, and it's just matter of time. I collaborate with colleagues, and then we find out what is the exact relationship between the two.
Joy, do you have something important? Because I'm having so many questions.
No, please, Harald, go ahead.
Okay, so what I think in relation to what you just said, Ahmed, is I have a statement or a quote from you. Tell me if I'm quoting you wrong, but as far as I understood, is that and this is topic of the next webinar actually, the inertinite benchmark of 2% is the only benchmark that has a temporal record supporting its residence time. I think this is very important in relation to what you just said, because it has, yeah, please elaborate on that.
There are only two proxies that I know of that are calibrated with time. You know, you're dealing with time. The most direct one is in fact hydrogen to carbon ratio. That is very well calibrated with the time and the residence time of biochar in incubation studies, which is great. But as I mentioned, if you assume that the peanut butter, the whole biochar is that peanut butter example that I said, so because there is a lack of empirical data for the actual inertinite fraction, the experiment, the duration of experiments are essentially short because of our life cycles, and they won't allow to see the degradation of inertinite. So for that reason, the actual empirical data is lacking the degradation of the inertinite fraction. So the second proxy that can actually answer this question, and it is correlated with a vast temporal record of the carbon through the geological time scale, is random reflectance, is the only one. In fact, geologists, if they want to measure anything that would relate to the basically the maturation of organic carbon, they would use the terminology of reflectance equivalent. That is, if you use Raman data for the geological rocks, you would ultimately report it as a reflectance equivalent, because random reflectance is the only proxy in the geology for organic carbon that is correlated with the temporal record of the rocks directly. Everything else has to be converted to the random reflectance in order to be compared with the temporal records.
I think that's a very important aspect and to understand. I'm just taking over. I'm very sorry because I just thought there's a question in the Q&A, and I'm getting confused between chat and Q&A. But Hans-Jörg here asked if there's evidence of deposits of inertinite in the living soil zone that are known to be very old. So it's kind of has something been deposited, like rather at the surface, and remained there in order for us to analyze and be sure that it has remained there for, I don't know, like hundreds of thousands or a million of years. I know there are some, what you said before, that there are parts of the sediment that have come up again and have been exposed to oxygen for a very long time. I think that kind of makes the case.
That, I mean, it depends, like how old is that surface soil, and knowing the age of the surface soil. If you find the inertinite in there, inertinite you could find anywhere. You could find in a soil, you could find in a deeper what we call it unconsolidated sediments, which could be terrestrial, that is soil or land, or it could be lakes or marine sediments. You would find it through virtually all records, sedimentary records, whether unconsolidated or consolidated. To geologists, soil is part of the diagenetic processes. It's part of it is that interval where the biosphere intertwined with the geosphere. It's not this isolated fraction. I mean, if you don't have soil, I mean, everything goes through this the soil and sediments in order to reach the geosphere. So you have to think about kind of broader rather than just only think of the soil. I understand the idea that the bacterial or fungi processes in the soil, they may have some tricks that we don't know as a geologist. And I give it to you. I don't have empirical data to prove, and so does anybody else. Nobody has empirical data showing that these processes, at least to be accelerated to go beyond 50%, 60%, 70% degradation of biochar in the soil. So in the absence of these, it's only temporal record, geological record that could help us by building a geological perspective of this material and how their permanence in geology could translate in what we are looking for in terms of the carbon storage.
Great. Thank you so much, Dr. Sané. Harald, thank you for helping to coordinate the questions. We're now at 2 o'clock, which is our hour is now up. So I want to thank and extend a big thank you to everyone who joined today. At points, we were over 160 participants, which is absolutely fantastic. So thank you again, everyone, for joining. Thank you, Hamed, for your time and expertise. And for all of you still here, we do have another webinar next week on February 26th at the same time, as well as for members, which would have a link in the newsletter for our members the following week on March 4th. So hopefully seeing everyone then. So thank you all and have a great rest of your day. Looking forward to seeing you next week.